Hi guys, this is Mrs. Gastler, and in this video we're going to talk about some applications of Newton's law of universal gravitation, which I write LUG because I'm too lazy. Okay. Alright, so we're going to start by talking about gravitational field strength. Okay, so this might be the first time we've talked about a field, but we have talked about field forces. Now, a field force, remember, is a force that acts without contact. Forces without contact, and that includes gravity, electric forces, magnetic forces, and those strong and weak nuclear forces. Those strong and weak nuclear forces, those are inside atoms, and they have a really short range, so we don't really talk about those very much. Magnetic forces and electric forces, their ranges are a little bit smaller, but gravitational forces can extend really far, and so they're not very strong, but because they extend really far, they have a lot more reach and influence than those other forces. So the gravitational field strength, what is it? It gives us an idea of how strong a gravitational force is in a particular location. So whenever we talk about a field, what we're talking about is the area that is affected by a field force, okay? I have a simulator that we'll look at in class, and I'll link it in Schoology, that is it can give you an idea of what it looks like. I'm going to try and draw one here in a minute, and it's not going to look very pretty, but we'll try anyway. To visualize that, what we do is we're going to draw the object, goes in the middle. So this is the source of our field force. Okay, that's our source. Okay. And what they look like is they look like arrows, so that represent the force, okay? So our gravitational field, gravity always pulls on the object, so anything that we put down is going to be pulled towards the object. So we imagine a test mass, so we'll pretend I'm holding a little test mass here, and I'm going to put it here. It's going to be pulled toward my object like that. And anywhere at the same distance, it's going to be pulled toward the object with the same amount. Maybe I'll make this arrow just a little bit bigger, okay? As I go further away from the object, it's going to be pulled less, right? So these arrows that are further away are going to be shorter, and I could draw lots of arrows, okay? There's an announcement. If you ordered from Jostens, go pick up your stuff. Now, if I get closer to this object, the forces are even bigger. So if I draw an arrow here, it would be even bigger than those other arrows. So if I put my test mass there, then that would be an even bigger arrow. That looks a little odd because well, don't put a dot there, okay? So that represents where my test mass is. So it's just a field, and what it would look like to you is arrows. You've probably seen in a video or on television when they have like a circle, and it's got they put like a sheet or a stretchy fabric on it, and they put like a basketball or a bowling ball in the middle, and it looks like it's going down. This is another visualization of a gravitational field. And so when they put a marble here, it's going to roll down in. And the further out, the flatter it is, so it doesn't roll out very fast, or roll down very fast. But the closer in you go, it's a lot steeper. So that is another way to visualize a gravitational field. Okay. So what you're doing is you're imagining if you put a test thing there, what would happen to it, and that's the kind of the forces that you would put there. Okay. So how do we measure a gravitational field? Well, we think about our gravitational force. Okay. So we're going to start out with Fg, and remember it's big G, m1, m2 over the distance squared. Okay. And since what we're doing is we're looking at a test mass, one of those masses, we'll call it M2, is our test mass. And M1 is the object that we're looking at as our source to figure out what the gravitational field is like. Okay, so I'm going to rewrite this, and I'm going to put the source right here. And I'm going to stick our test mass over here and put our d squared right there. So this right here represents our gravitational field strength. Now, we're going to do a little bit of magical stuff right now, okay? Now, there's this other formula that you might remember from another time in your life for the weight of an object, okay? Remember Fg equals m times g? If I rewrite it as g times m, do you see a similarity to the format here? Do you see it? Do you see it? There's Fg, there's m. Do you see the similarity right there? It turns out that this g, that acceleration due to gravity, acceleration due to gravity, is the gravitational field strength. And that 9.8 meters per second squared is at the radius of Earth. So G equals big G, mass of the source, over the distance squared. And on Earth, running out of room here, on Earth, we would use the mass of the Earth, big G, mass of the Earth, the radius of Earth squared, okay? Now, let's see, the mass of the Earth is like 5.98 times 10 to the 24th. And if I remember correctly, the radius of Earth is 6.38. You should double check this though, times 10 to the 6th meters. I'm going to see if it's in this book right here. That does not, wait, hang on, maybe it's on the back side. Nope, I don't have it in that book right there. So I don't have those values. You should look those up. You could actually calculate G from these values and see if it is actually 9.8, okay? It's a fun thing. That's where that G comes from. So G is the gravitational field strength. So we could add that up here. G, okay? G is the gravitational field strength. G tells you how big or how strong the gravity is at that point. So G 9.8 is the gravitational field strength on the surface of Earth. You should do a fun calculation. How strong is it on, how strong is G at the International Space Station? And why don't they feel it? All right, so connecting gravitational field strength to kinematics. This is something that you're going to be asked to do in lots of AP test questions because that's what they like to do. So remember falling objects? So that's really it. So what they like to do is they like to say, well, we went to another planet and this is the data that we got. Okay, it's just kinematics data. So they're going to take the data that you had, like V and V naught, the final velocity, the initial velocity, and the time, and they'll give you like a graph. The acceleration is just G. That's all I've done here. I've replaced the acceleration with G, and we're talking about things falling. So these are all velocities in the y direction, okay? So here's the next one. This is that sometimes I was writing this one, D equals V naught T plus 1/2, that's a T, A T squared, and now it's in the y direction. That's the only difference, okay? With G, A has become G. So anything that you did in Unit 1, this was back in Unit 1, okay, works here, except you're using G for the gravitational field strength. So whenever it says, can you find the gravitational field strength on this planet? Yeah, you can. Use basic kinematics and calculate the acceleration of the object as it's falling. Find the acceleration of a, let me write that out because it's got the word A in there, of a falling object to get G, okay? I made a note under here, things fall down, so you have to be careful of your signs. Be careful of positive and negative, okay? As long as you know which way is positive and which way is negative and your signs are this matching for whichever way you have chosen, then you're good there, okay? Up next, I just wanted to talk briefly about energy and satellites and planets. So remember, the total mechanical energy is the kinetic energy plus potential energies. In this case, we don't have any elastic potential energy because it's not stretchy, so we just have gravitational potential energy. when it moves further up, remember we had MGH as our gravitational potential energy, but when that's kind of really only on the surface where that's useful. Yeah, they really want you to get your capping down, seniors. Okay. If we take, we can actually take this formula and we can replace this for our planets, because this is kind of on the surface with that H. If we replace G with big G, M Earth, over R squared, and that H is really just R as well. We'll put an R there, okay? Then UG is now big G, M1, M2 over R. Okay, see one of the R's canceled out. So this is kind of our new planetary, this is a planetary scale gravitational potential energy formula that we can use. Okay, so when we look at this here, as we move out, it's going to look a little bit weird, but we're still going to be doing the same thing. The kinetic energy, because it's slowing down, I shouldn't have shown you that yet. With the kinetic energy, as it's coming out here, it slows down, so there's less kinetic and more gravitational. Yeah, I shouldn't have shown you that one yet because it's going to make not much sense. And then it's going to come back down here, but the total kinetic or the total energy is the same. Here it's got more kinetic energy and less potential energy. Oh, I know why. It's got a negative. I can't. This is negative. The negative in here comes from calculus. Calculus. It's not just a plain old... Not just plain substitution works there. If you want, I can show you where that comes from. It's an integral, okay? But a negative shows up because of the way you're moving. So when we do move out, because the R is changing, it's still going negative, we get less negative, okay? So on a number line, here's 0, and we went from, we get a small, we go in a way that we end up with actually more because it's less negative. Does that make sense? And that's why we have more potential energy and less kinetic energy as we move. But we're still, energy is conserved. Okay. And so that is something to think about when objects are moving. Okay. This isn't an elliptical one. We are talking mostly about circular ones, but should questions arise, that will help you answer them. Okay. All right, that's all I have to say about applications of Newton's law of universal gravitation. If you have any questions, make sure you ask. And that's all I got. All right, thanks for watching.